So now we're going to look at what are called annuities, but the way we're looking at annuities here is a way that you'd use them as a savings plan, which is where every period, whether it's every year, every month, every week, you make the same payment into the bank. And what's going to happen is it's like you're setting up a different payment each time to go in from your own money, but also any money that's already in there is going to collect interest at the end of that period as well. So your new money comes in, that increases the principal after you've gotten the new interest for the previous period. And it's just going to keep piling on. And so there are two kinds of problems that we have here. We can say, what if I put $100 a month in? How much will I have, let's say 30 years down the road? And you can find out the big number that you're going to have at the end by all of that savings, which includes compound interest. Or you can say, I need to have $1 million by 30 years from now. And I want to put in a little each week. And you can solve a formula that'll say, how much does each payment have to be so I get to that goal? So those are the same formula working forwards and backwards as a lot of people think. But sometimes you know what you have to put in and you want to see where it's going to take you, and that's fine. But a lot of other times it'll be, I know what I need to have to retire and how much do I need to put in. And whichever one you need to do will be the problem that we're going to look at. So I'm going to let you know that savings plans are used to reach a set goal or to contribute a set amount. But what's going on with savings plans require a periodic payment. And I had said this earlier, P would eventually mean payment rather than principal. P is always your own money, but it goes in pieces when you're doing it as a payment. You're putting in a little bit each time, and it functions each period as new principal, and the other stuff is going to stick around as part of your account balance. Over a set amount of time, not that kind of time. It's not the spice. All right, time, which is n periods. At a fixed interest rate. And that rate per period, it'll be the APR, then divided by 100 and divided by the lowercase n. Lowercase n will be a number for weekly, monthly, however it's going to go. If it's annually, it's once per year, and since it's an annual payment, you divide by 1 and you get to leave it alone. This is division by 100. Come on, Jeff. Okay. There you go. So you're going to do divide by 100 because it's percent, divide by n if it's not annually. If it's annually, you can divide by 1, it'll stay the same. Monthly is 12 times a year, weekly is 52 times a year, daily is 365 times a year. That number will go in. My recommendation, and you'll see it in the work that we do, will be if that plays out to a decimal that terminates, go ahead and write the terminating decimal. If it does not, write the entire formula out and use your calculator to hold on to all the digits you can. Don't find yourself rewriting all the digits because you may cut it off too early and get the wrong answer by not going far enough in. So just let the calculator do as much as it can do for you. And what we're going to do is we're going to find there are two formulas. There's the future value is called the account balance. And I capitalized the A because it's going to be A. And our formula is going to be that we have A equals P times, I'm not going to derive the formula for you. I can say, trust me, I could. I can say, don't trust me that you don't think I could. Neither of those matters. What's very important is the work we get done with this formula, not the way it's derived algebraically, so I can feel like, look at this fancy algebra, everybody's following me, right? And you all like nod with glazed over eyes and pretend you know what I'm doing. And then in the end, you're like, so that's the formula? And that's all you write down anyway. So here it is. We're going to have P times 1 plus capital R, close the parentheses, take it to the power n, and then subtract 1. Sometimes I get people saying, why is that minus 1? And this is one of the very rare times in all the times that I teach math that say, it's not worth it for me to derive the formula and show you why this is what does the job, but I am going to show you that it works. We're going to use Excel to do that. So the other formula that we can have is if I multiply both sides by R and divide by the square bracket, we'll find out that P is equal to A times R, and then it's going to be divided by the square bracket of 1 plus R to the power n, and then minus 1. And those are the two formulas that we have, which we'll keep right here on this board for our uses as we're going through and doing problems. But really, the two things that we're going to work on here with annuities are going to be, I know how much I'm putting in every period. Tell me how much it's going to be worth. Or the other way is I have to get to this goal, but I'm going to put in a little each period. And you can't miss a period. You don't have to double up or anything like that. You've got to stay with every period. So that's why they say for retirement, they say pay yourself first. It's far too easy to say, oh wow, this month I can't save for retirement because I got to spend on this or this or this. Pretend that the money you're saving for retirement is gone before your check gets home. And so they will withhold money for retirement for you and put it right into your retirement account, so it's not a part of your take-home pay, because the money always does seem to go for lots of people, and then they never do wind up saving anything for retirement. So that's what we're looking at. We have P, which is our payment instead of principal, but it does the same thing. It's your own money going in. We have N is the number of periods, right? N is, we're going to take, the fact that it was equal to how many periods per year times the number of years. We need that capital N. We're going to need to have the interest rate. This is R, the interest rate per period, and that thing is called R. We're going to need our periodic interest rate. You can't just throw the APR in there. Got to deal with it being a percent and deal with it being a certain number of periods. And then the future value is, again, the account balance, but it's where the account balance is going to be. You don't look at it in the middle, you look at it only in the end. So no matter what, with some erasing, we might lose this. I'm going to bring this in and have just the part that's got the formula visible on the screen for you, so that it's there the whole time as I'm doing work back here. To let you know what we look for is we need to make sure that we know all but one of the variables. And the thing to do is the one I'm looking for is the one I don't know. That's why I'm looking for it. So I need A, P, R, and N to get this job done. 3 of them will have to be numbers I can use, and 1 is the number that I'm looking for. And so we'll take a look at how these problems run out. It says, how much will you save if you put $150 per month into an annuity, which is your savings plan, if it has an APR of 10.2%. Remember, we had about 10% away for 40 years. 10% APR, we went for 40 years and we put it away. We put like $22,000 in, it became $1 million. But to do that, you got to have the $22,000 right now, drop it off and forget about it for 40 years. And a lot of us don't do that. This might be a little bit more achievable. Let's see what we get in terms of money. If we put $150 per month away, that's P, that's our payment. But that's P, that's our own money going in. And it's going to have an APR of 10.2%. Wow, I didn't tell you for how long, right? So let me just look at this. I think I said it, but I didn't write it down. Over 40 years. Okay. And so that when I look at this, I come back and I have all the numbers that I need. First of all, I'm looking to find A. So I'm going to use this formula. I want to find the account balance in the future. I'm not doing this one where I need to know A in order to find P for the principal. I know, or in this case, the payment. I know the payment is going to be $150. So P is equal to each time I'm putting in $150. And that's it for the payment. That's my own money going in, but it goes in a bunch of times. APR is going to help me get the R. Here's the APR of 10.2. That cannot go in. I need to divide it by 100 for percent. And then because it's monthly, I have to divide by 12. That makes sure I slice down the APR to a smaller amount that's going to be applied to the existing balance every time I have a new period, which in this case is every month. And N is equal to how many payments do I make? Now 40 years is the number of years, but then this is going 12 times a year, so I actually do my 40 times 12, and that I can determine to be 480. I'm going to grab my calculator and see if 10.2 divided by 100 divided by 12 works out to a nice decimal that I can work with. And so I'll go ahead with 10.2, and I'm going to divide by 100, and I'm going to divide by 12. This time it's going to be 12 because monthly payments happen 12 times a year. Now you have to make sure that you get it right. That's always kind of true, but 0.0085. That's my interest rate. My APR is 10.2. My decimal rate for the year would be 0.12, and I wind up dividing that by 12 to see what it is for each month, and that's what's going to go in for R. And this is the method that I'm going to use through all the formulas that we have. Get me a capital P, which is your own money. Get me an R, which is your interest rate for each period, and get me a capital N, which is the number of periods all the way through. Now let's put that to work right here in this one. So I'm going to take down the formula. We're going to use it. We're going to make a determination on our calculator to what it equals. So it's A equals, P is $150, parentheses inside of a bracket, and there I have to go with 1 plus, and this is 0.0085, so I could write that as 0.0085 right behind the 1 in this case, but sometimes, since that doesn't terminate as a decimal for us, we will have all of this stuff to go in our parentheses and let the calculator get it for us. To the power n, which is 480, then down here minus 1, and close our parentheses. Then in the denominator we have R again, 0.0085. So depending on how much you paid for your calculator and how well you know how to use it, you can use some of these values that are here. But what I'm going to do is I'm going to determine the numerator, and then I'm going to come back and divide while it's sitting there by the 0.0085. So what I have here is 150, now I'm using a dollar store calculator, all right? $150 times, I open the first set of parentheses, I open the second set of parentheses, and I don't know if that's going to work on this because it was a cheap calculator. 1 plus 0.0085, and I close up those parentheses, and I raise it to the power 480, and then I do subtraction by 1, and I got something that looks a little crazy. So I can't do that with this. But if your calculator is better, you can do that and have multiple levels of parentheses. Instead, I need to make this into 1.0085. So I'm going to have that as my only pair of parentheses. So I'll show you what I'm doing in this particular case. But there's a way to do it. Even without parentheses, there's a way to do it. So if I want to do this one, I'm going to start inside the parentheses and go with 1.0085, and I'm going to raise that to the power of 480. Then I'm going to take what that result is and subtract 1 from it. Right now I'm looking at 57.1344. I'm going to multiply that by 150. So I have the numerator completely done. And now I'm looking at 8570.16, and I'm going to divide that thing by 0.0085. And I come out of here with 1008254. 186, and the decimal goes here. So I'll put in my commas, and I'll see that that's $1,008,254.19. And now that's worth looking into and understanding, not saying, hey, I got the right number, I don't know what I did, but I'm going to get an A. What we have here is the fact that if you can get 10.2% as your rate of return on average for your deposits that you make over 40 years, as long as you put in $150 per month for 40 years and you don't miss any months, you don't have to do any extras, but put it in every month, let the interest do its thing as part of this annuity, you'll have it worth over $1 million when you're 40 years from now done. So if you're 22 and you plan to retire when you're 62 and you get into a plan like this by putting in $150 per month, then you'll have $1 million when you retire. And that's real. And we'll look at why that is when we get to Excel in a little bit, but that's what that's doing. Now, if you have a fancy, expensive calculator, you can do a lot of this stuff to determine what the numerator is. I'm going to do this. I had done, what's inside the square bracket. First, I did this to that power, then -1. I found out what that equaled. And then I multiplied by 150 and I divided by that. That's fine. But if you want to do it with parentheses, you can go 150 times and open up a single pair of parentheses and put in there 1.0085, raise it to the power of 480, and then subtract 1, and then close your parentheses, and your entire numerator is done. So if you want to hit equals, you'll be looking at 8570.16, and then you'll divide that by 0.0085, and you'll get to the number. So that's how that works. Okay. That's how much it's going to be worth. So that's one of the two things we do with annuities. We do have to say, all right, how much do I put in each period? Usually that's given to you. You may have to do some computation in certain types of problems to see what each payment's going to be, but that payment is going to go in as a number for how much each period. This, if it starts as an APR, definitely get it down to a decimal. So I always say divide by 100 for percent, and divide by, give me a number that works there for the kind of payments you make. This is every month. Months happen 12 times a year, so you divide it by 12, make a smaller rate for what you're paying, and then do it not just 40 times, but 40 times 12, because you're going to do 480 payments. And those are numbers that are going to drop in for that. So that's how we get that $1 million for $150 per month, right? So you're like, well, how am I going to put $150 per month away? Well, if you get paid twice a month and they take $75 out of your paycheck for retirement and do this for the 40 years, then you'll get there. But better yet, a lot of times they'll pay half and you'll pay half. So now you'll be putting in, since it's got to be 150 a month, it's 75 from you per month and 75 from the company per month. Across 2 checks, it's less than $40 per check. And because they match it, you'll get to that value of $1 million in retirement. So that's why you want your retirement money taken out before you see it. Otherwise, you won't say every month go down and take $150 out of your wallet and put it into retirement, because people just as a tendency don't do that. So what we came out with was the account value was 1,008,254.19. That was it. $1 million, $8,254.19. It went a little bit over. That's fine. How much did you contribute? So how much of your own money went in? Let's forget that the company might put the money in. Let's say you did have to put the $150 in per month yourself. So we got $150 times 480. That's times 40 times 12. This is 40 times 12. That's the number of payments that you make. So what we're going to get here is 72,000. So over the years, $72,000 of your own money went in to become that million, along with other money. So now I want to use the other formula, this one that says P equals AR, right? P equals AR over the square bracket, which is going to contain 1 plus R to the power n minus 1, and show that that formula also works. So now we know we want to get to $1 million. So in this case, we want to get our account value to be $1 million. We're going over it a little bit, and therefore we won't have to put in exactly $150 to reach the million. It'll be close. R is still going to be equal to 10.2 divided by 100 per percent, divided by 12 for the month, and therefore we're going to get, once again, the 0.0085. And N is, again, 40 years times 12 months a year for 480. And therefore, when we go for this one, we get $1 million on top times the interest rate of 0.0085 over, and then down here, we have the 1.0085 powered to 480 minus 1, and close that off. So let's see what we get here. I'm going to work on 1,000,000 times 0.0085. It's going to have the 85 in it because it's really just going to make the decimals move to make it bigger. But anyway, it's 0.0085 times 1. 1, 2, 3, 4, 5, 6 zeros for the million and $8,500. Because the first 1, 2, 3, 4 moved to 85, 5, 6, yeah, $8,500 is what that is. That by itself doesn't mean much. And now I apply what's going on down here. I've got the 1.0085 powered up to 480 periods. I get what that equals, and I will subtract 1 from it. And I got, if I write what this has, 5.713440,387, that's probably going to go far enough to get me accurate to the penny. But let's see what I get. I'm going to start with 8,500 and divide by that number. So I'll type that into my calculator, 8,500, and then divide by the decimals as I have written there. So, and I'll come out of there with $148.772. Which means $148.77 should get me there. Actually, $148.77.2 will get me there. So I'm going to use $148.78 to make sure I go over $1 million instead of coming up short. And that's the other use of the formula. It's really, the major formula here is used forwards and backwards. I think it's forwards to look for the big number and backwards to look for the smaller number. Let's see. So that's approximately $150 per month, right? Going to quibble about $1.22 per month that you actually should get back. So maybe go ahead and put in the $150 and reach this instead. Pick up the extra $8,000 at retirement from that little bit that you put in. But that's the power of compounding. But here you're only putting in a little bit. You don't have $22,000 to drop in right now and go back to when you're 62. You got to do this as an annuity, and that's what annuities are for. To let little numbers go in over and over again over a long period of time to do their job. And really the first deposit is in there doing its thing, and then the second deposit starts 1 month later and it does its thing. And really what you have is 479 different deposits that you made that run along and make growth. But this formula keeps them all piled in together. Okay. Now let's look at something that is more appropriate for a shorter term savings. You need to save a certain amount of money so that you can spend it in the near future. And so you're going to put money in a little bit at a time, or maybe it's not that little bit at a time. See, this 40 years every month, that's a lot of payments. You did see it was eventually $72,000 of your own money. All the rest was interest. So you could subtract and see how much interest you made. But how much must I put away per month? At 1.5% APR to save $6,000 over 2 years. Now we're going with this being monthly, right? It's per month, so it's going to be monthly when we do that. So let's figure out what we've got in terms of what we need. We need to have an account balance of $6,000. So we do know A is going to have to be $6,000. That's what I'm trying to get to. I want a smaller payment. I don't know the payment yet. R is 1.5. Divide by 100 for percent and then divide by 12 because it's monthly. And N is 2 years, but you don't put in 2. You do 2 times 12. You get yourself 24 periods. Let's see how this value turns out for R. I got 1.5. Divide by 100 for percent, and divide by 12. And again, unfortunately, it's 0.00125. So I'm able to write that out. But if your decimal continues to run off screen on your calculator, you're going to want to keep all these values in place as you do your computation. So anyway, we're trying to find out what P equals, and P is equal to A times R over the big parentheses, right? You don't have to remember it, right? You do get a note card to put the formula on, but you do need to know which kind of thing is going on. And so this is, I'm putting away money per month. That makes it an annuity. I'm saving my own money to try and get there. I'm also getting interest, and I'm trying to find the payment because I know I got to get to 6,000 as the big goal. So now this will be the 6,000, goes in there, and then 0.00125 there, and here we got 1.00125. It might be 1 plus, 1.5 divided by 100 divided by 12 and close the parentheses if necessary. Raise to the power of 24 and then subtract 1. This is 1.5%. This is not 10.5 or something like that in terms of percentage rate. You're also only saving it for a couple of years. But here we go. The top will be 6,123,000 times 0.00125. The top turns out to be $7.5. By itself, it doesn't mean very much, but it's something to contribute to the formula. As we go for the bottom, where we've got 1.00125, and we're going to raise that power to the 24th. Raise that base to the power of 24, and we're now going to subtract 1 from that. And all of that stuff gets me a number that looks like this, 0.0304. And if you stop with too few decimal places, you're going to get a wildly wrong number, right? 0.03 might not do this job very well. 0.0304, 35229. Now, I want to show you why we use all the decimal places. So I'm going to take that 7.5 and divide by that number. And I'm going to come out of here with 246 and 42.5, well, let's see, dollars. 246.424. So I guess what I'm going to go with here is 246.4. Now rounding it off would say 42 cents, but that's actually going to come up short. So rounding it off, I'd go 42, but in reality, I'd probably go 43. Pay extra so I get there, and then the last payment will not be quite as big. If you come up short on the last payment, you're going to owe money when you finish it out. So, but going with rounding off, I'd go with 0.42. And so we got this $246.42. And that's your payment per month. You're going to do that for all 24 months. How much do you contribute? We're going to take the 246.42, if you want to go with that, times the 24 months, and you get an amount for that. So this would be another part of the question. So we go 246.42, multiplied by, in this case, 24 payments, and we're looking at $59.1408. How much interest did you earn? Well, you started with $6,000 that you had to get done, and subtract all the money that was your own. And here you'll see that that's going to be 92, that's a 5, that's an 8, and $85.92. Over 2 years, you made that amount of interest. So by putting the money in a little bit at a time, you got $85.92 from the bank for doing those payments as you went along. Not a big contribution, but the other thing you could have done was you could have taken $250 every month and just dropped it in the drawer at the top of your dresser, and at the end of the 24 months, you'd actually have the same $6,000. But by dropping it at the bank or having it taken out of your check, you did make a small amount of interest because you had a small interest rate at that point, a realistic interest rate for what sometimes is going on now, and you didn't do it for very long. So that's what those will do. We'll see some more in the homeworks.